Cancer cells are masters of disguise and deception. They appear to defy the laws of nature, growing and multiplying with reckless abandon. But even cancer cells have an Achilles heel. Their survival depends on a constant supply of energy. To fuel their rampant growth, cancer cells undergo a metabolic transformation, a cosmic shift in how they generate energy. Normal cells typically rely on a process called oxidative phosphorylation, occurring within the mitochondria, the cell's powerhouses. This process efficiently breaks down glucose, producing ample energy. Cancer cells, however, often switch to a less efficient process called glycolysis. This phenomenon, known as the Warburg effect, allows cancer cells to thrive in low-oxygen environments and produce building blocks for rapid growth. Imagine a bustling city at night, its skyline illuminated by countless lights. That's oxidative phosphorylation, a beacon of efficiency. Now picture a city shrouded in darkness, relying on flickering candles for light. That's glycolysis, a less efficient but necessary adaptation in the cancer cell's shadowy world. Understanding this metabolic shift is crucial to unlocking new strategies for combating cancer. By targeting the pathways that drive the Warburg effect, we can potentially cut off the energy supply to cancer cells, starving them from within. At the heart of the Warburg effect lies a critical enzyme complex known as pyruvate dehydrogenase, or PDC. PDC acts as a gatekeeper, controlling the flow of fuel into the mitochondria for oxidative phosphorylation. However, in many cancers, PDC's activity is suppressed, effectively shutting down the mitochondrial powerhouses. The culprit behind PDC's inactivation is another enzyme called pyruvate dehydrogenase kinase, or PDK. PDK acts like a wrench thrown into the cellular engine, preventing PDC from doing its job. This inhibition of PDC forces cells to rely more on glycolysis, fueling the Warburg effect and driving cancer cell growth. Imagine a train carrying vital supplies to a city. PDC is the engine, powering the train towards its destination. PDK, on the other hand, acts as a saboteur, derailing the train and cutting off the city's supply line. The PDC-PDK axis represents a prime target for therapeutic intervention. By inhibiting PDK, we can potentially reactivate PDC, restoring the flow of fuel to the mitochondria and reversing the Warburg effect. This could have profound implications for cancer treatment, essentially cutting off the energy supply that fuels cancer cell growth. Enter dichloroacetate, or DCA, a small molecule with the potential to disrupt cancer's metabolic machinery. DCA acts by inhibiting PDK, effectively removing the wrench that's jamming the cellular engine. This inhibition allows PDC to function normally, reopening the gateway to mitochondrial oxidative phosphorylation. Think of DCA as a key that unlocks the mitochondrial powerhouse. By inhibiting PDK, DCA allows the cell to breathe again, shifting its metabolism back towards oxidative phosphorylation and away from the inefficient glycolysis that fuels cancer growth. This metabolic shift has several important implications for cancer cells. First, it reduces their dependence on glucose, potentially slowing down their growth. Second, it increases their sensitivity to oxidative stress, a vulnerability that can be exploited with other therapies. DCA's ability to flip the metabolic switch in cancer cells has generated significant excitement in the research community. It represents a novel approach to cancer treatment, one that targets the underlying metabolic abnormalities driving cancer cell growth. The Warburg effect not only alters the metabolic landscape within cancer cells, but also shapes the environment surrounding them, known as the tumor microenvironment. This environment, characterized by low oxygen levels and high acidity, plays a crucial role in tumor progression and metastasis. One of the byproducts of glycolysis is lactic acid. As cancer cells ramp up glycolysis, they release large amounts of lactic acid into the tumor microenvironment, creating an acidic environment that promotes tumor growth, angiogenesis, and immune evasion. DCA, by inhibiting PDK and shifting metabolism back towards oxidative phosphorylation, can help to reduce lactic acid production, effectively taming the lactic acid beast that contributes to the tumor's hostile environment. This metabolic shift can potentially make the tumor microenvironment less hospitable for cancer cells, hindering their growth and spread. Imagine a swamp filled with toxic fumes representing the acidic tumor microenvironment. DCA acts like a breath of fresh air, clearing the toxic fumes and making the environment less conducive to the survival of harmful organisms. By modulating the tumor microenvironment, DCA could potentially enhance the effectiveness of other cancer treatments, such as chemotherapy and immunotherapy, which often struggle to penetrate and eliminate tumors in such a hostile environment.